So in the first video, I managed to set up the Oliver app with its free local models and then pre-prompted it with a model file so that it could chat and talk about the information I provided. And I also tested it with different temperatures. And then later on, in the second video, I connected 3 nodes using the Meshtastic LoRa protocol, which was a big breakthrough in terms of RF telecommunication. Now I'm planning to mix these two concepts into one idea, and with a few extra tools here and there, I think it could turn into a fantastic project. So starting with the first step, I'm connecting these two AI models and letting them chat through the mesh nodes. In this kind of setup, the two models sort of swarm together, and they create this really dynamic exchange of ideas. As you can see, the model touches briefly on the chosen AI topic before drifting into small talk and polite chatter. Don't get me wrong, we do want it to be friendly, just not in a way that feels dull. Since I haven't set up a model file with a tailored pre-prompt yet, it's still running without that guidance. In this step, I went to the official MeshExec GitHub repository to download the top file. Using 7-zip, we then extract it and configure the commands that will be used. The AI model is now pre-prompted with a model file containing all the commands I generated from the configuration file on the second machine. This gives it a clear understanding of the tools that we'll use. The next step is to implement a Python server that accepts user text input, translate into the appropriate tool command via AI, send that command across the mesh network to the target machine, and return the result, all triggered by a simple prompt from the controller machine. With this setup, the AI can now display the requested data based on user prompts. Now I can retrieve system information or run diagnostics remotely. In this step, MeshExec retrieves sensitive information from the second machine, such as IPv4 and VIX addresses, and MAC details. Naturally, I won't display those here. Only general data like timestamps and basic logs will be shown. Now I've set up the MeshExec feature, which allows a mesh node to control the second machine it's connected to. By doing this, the node can execute commands on that machine, granting access to the system and allowing the retrieval of sensitive information. The next step is to implement a Python server that accepts user text input, translate into the appropriate tool command via AI, send that command across the mesh network to the target machine, and return the result, all triggered by a simple prompt from the controller machine. With this setup, the AI can now display the requested data based on user prompts. There you go, nice and clear with a natural tone and easy pay. This data can then be collected on a controller machine where an AI system analyzes it to enable automated alerts when critical thresholds are reached. And in its current form, MeshExec provides controlled access, but establishes the foundation for automation. The AI now has visibility into system states and can act on them, gradually evolving from simple monitoring toward autonomous operations. There you have it. The idea behind my setup is to use MeshExec as a lightweight remote execution layer over Meshtastic. It allows one machine to issue predefined commands to another by configuring command aliases in a configuration file and sending them across the mesh. Now we're going to use the already built RadioLM implementation and compare between it and the one I created earlier. So this RadioLM system transforms a standard Meshtastic node into an intelligent AI-powered assistant that can understand natural language and execute commands over the mesh network. The implementation began by establishing a dedicated directory structure. A YAML configuration file was created to specify the AI model, which was DeepSeek R18B, the one being used, since Gemma 3.1b doesn't support tool use or function calling. This DeepSeek model defines available tools like keyboard typing and emergency alerts. The core of the system consists of several Python modules working together. The first Python script handles Meshtastic communication and message routing. Python script manages per node conversation contexts and states like new chat, normal chat, chat with LLM, echo, and the model modules handle AI interaction through a llama. The system automatically chunks long responses to respect Meshtastic's 200 character limit, maintaining separate conversation histories for each node. So the first thing I'll be doing is enabling the LLM model, then greetings, asking about his potential. Now I will be asking about the specific date. There's no way it will get it right because it is not connected to the internet. Now I'll test if it has the memory as I was told by saying what my color is. Let's see if /tools works. Asking about the color again. /enable echo, and this should bounce back. Here goes. So if I'm being real, this setup are better to use, and it has a few more things my setup doesn't have. On the other hand, my setup has more commands to execute thanks to MeshX. It uses a fast model like Gemma, but it doesn't have long memory over the conversation like the radio LLM has. So I'm thinking maybe I could implement these two setups to make radio LLM use MeshX. Feels creative enough. So to make a quick recap about what I did on this video, first, I managed to make 2 AI models chat through the mesh network. Secondly, I used meshexec to get some sensitive data about the second machine. Then I fed the commands to AI Gemma 3. And finally, I tested an already built model, radio LLM with Quinn 3. Then coming up next video, I'll start imagining new scenarios, starting with combining meshexec and the radio LLM model into one process. Good guy.